In this video, I'll be talking about PN diode equation. Now, obviously, the name is itself suggesting that we are talking about a PN junction. We have a PN junction, we understand it has P region, it has N region, it has depletion layer, and in P region we have a majority of holes, and in N region we have a majority of electrons and minority of holes. And here in P region we have minority of electrons, and we have depletion layer or depletion region. And what we are trying to do here is we are trying to treat this PN junction through the classical statistical mechanics, and we understand that classical statistical mechanics was completely established in terms of Maxwell-Boltzmann's distribution. Maxwell-Boltzmann distribution. And using Maxwell-Boltzmann distribution, we can have statistical values for velocities of molecules within certain range, say v and v plus dv. We can have momentum range of values, the average values of momentum, and many other physical quantities that could be calculated using Maxwell-Boltzmann's distribution. And we understand the basic mechanism of biasing of a PN junction, and we understand if we bias it in positive, in forward direction, then the role is taken place by holes from P side and electrons from N side, and there is a minority role also from P side to N side at the depletion region. Now, so certainly we are taking this PN junction system as a classical system. So that's why we will be making use of Boltzmann distribution function. And we would like to symbolize certain things here, like say if I say n of n, this is number density of electrons in N region, and similarly if I say N of P, it represents the number density of electrons in P region. So we can similarly think in terms of holes as Pn. This will give me the number density of holes in N region, and P of P will give me the number density of holes in P region. So keeping these things in mind, we can write down the Boltzmann distribution function for these two regions, for these charge carriers. So now making use of using Boltzmann equations. Now, for electrons, we have n of n divided by n of p, and this is given as e to the power of minus ev by kBt. So KT I will write simply here. And this E refers to the charge, and this n of n by n of p, it is plus e to the power of ev by kt. So this k is it is Boltzmann constant, right? So we are treating this system in classical fashion, Boltzmann constant. And T is the temperature, right? And we have V, and this V will be we have the barrier potential in absence of biasing a p-n junction. So this V refers to that barrier potential. So this V is barrier potential. So this basically gives me the ratio of electron densities at the junction, at the depletion layer. So this is the ratio of electron densities at depletion layer. Okay. Now, similarly, we can have this Boltzmann equation in terms of holes. So P of n, if I go with P of P by P of n, that will be equal to e to the power of EV by kBT, right? So we understand the difference here. So this P of P and P of N, it gives me the ratio of hole densities at depletion layer. All right. So this is my ratio of electron densities, and this is my ratio of hole densities at depletion layer. All right. So now these two equations, if I call this as equation 1, if I call this as equation 2, these equations are known as Boltzmann's equation. Now, when we apply a potential difference across this p-n junction, right? So, in order to differentiate that potential, I should use a different notation here. I will use here VB. VB refers to the barrier potential. It will be nice if I now when I forward bias this p-n junction, what am I doing? I'm applying a voltage equal to V. So this here is VB, and we are forward biasing this p-n junction. And when we forward bias this p-n junction, there certainly will be modifications. I mean, in case of forward biasing, the resultant voltage that we will have at the barrier, at the depletion layer, that will be VB minus V. Because this potential, as we understand that the potential barrier, the width of this potential barrier decreases. So if I have to quote it this way, when we apply this small potential to the junction with positive terminal to this P and negative terminal to the N, the potential barrier reduces. It reduces by this much of amount, and the mobile charge from the source it goes to the depletion region. electrons are added to n, and holes are no, electrons are added to the p region, and holes are added to the n region. So the current, if we talk about the current that is far from this junction, that's far from this junction, it's due to majority carriers, and the diffusion at this, and the diffusion at the junction is by the minority charge carriers, predominantly by holes in the n region. Thus, under the forward bias condition, these equations that we have for hole densities, if I go with the hole densities on the right side of this p-n junction, there is a modification. So what happens to that equation, to this equation? It will be modified under the forward biasing of p-n junction. So in order to proceed from here, so what am I going to write here is, I will have, say, here I will have Pn, okay, plus delta Pn. So I would like to introduce this change, and this will be equal to, this will be P of P, e to the power of minus e times VB minus V times divided by KBT. I'm not writing B here. K is for Boltzmann's constant and T is for the temperature. And we can substitute for this Pn from this equation again, right? So what we can get here, we can get this delta Pn. This delta Pn will come out to be, it will be P of P e to the power of minus EV by, it has to be, let me get that EVB here, EVB by KT, okay, EVB by KT, and inside you will remain with e to the power of EV by KT minus 1. Okay, so by making use of the modifications, when we forward bias this p-n junction, we will have delta Pn, and this delta Pn will give me the whole densities on the right side of this n region. That will be given by the measurement of this delta Pn, and using the similar analysis for electron densities on the left side. Okay, so here we will have electron densities, here we will have hole densities. So for electron densities, using the similar analysis, what are we going to get? So similarly, I would like to write here, similarly for electron densities, where for electron densities in p region, what will I have? I will have the same kind of thing. It will be n of p plus delta n of p equal to n of n e to the power of minus times e of VB minus V by KT. All right, and this can be equal to, we can change it to n of n e to the power of minus EVB by KT times e to the power of EV by KT. Now this VB is the barrier potential in absence of forward biasing, and this is the amount of potential that's added to the system, that is V. So using the similar thing that as we did for hole densities, we will be able to calculate this delta N of P, right? And this delta N of P is N of N e to the power of minus EVB by KT. Looking from this side, okay, then it will be e to the power of EV by KT minus 1. All right. Now, what can we talk about here is we have calculated the electron, the hole densities in the N region, and we have calculated the electron densities in the what we call as in the N region. So we have delta Pn as electron densities in the P region, and we have delta Np hole densities in the N region. Now let's go back to that equation that we have already developed, the equation for the current that flows through a that moves in a semiconductor. And what's that equation? That is I is equal to J times A. Now, because we understand that current density is current by area, and if you rightly remember, we calculated the conductivity of a semiconductor in presence of potential difference, and if you rightly remember that we had there n of it was a number of holes times the drift velocity of holes plus number of electrons into drift velocity of electrons. The same equation we will be using, but instead of number density of holes and number density of electrons, we will be using delta Np and delta Pn. So these equations will be marked there. So if this is equation number 3 and this is equation number 4, so what should I do now? I should write down this equation as the current, okay, the current that we will have here. This current is I equals A E times, it is delta Np VE plus delta P delta Pn VH. If you rightly remember, we have an equation I equal to A times E times N of N V of E plus N of H V of H. So this kind of equation we are making use here to calculate the current, right? Now, when we will substitute for this delta Pn, we have delta Pn here and delta Np here, we have delta Np here, we have delta Pn here, and when we'll substitute these two equations, substituting 3 and 4 in 5, what we are going to get is we are going to get something like I is equal to, there will be cancellations, it will be AE times N of N VE plus P of P then VH times e to the power of minus EVB by kt times e to the power of EV by kt minus whole minus 1, right? So this whole thing here, this whole thing is substituted for the saturation current. This whole thing is called saturation current of PN junction, and that is symbolized as IS. So what are we going to get from this equation is this current is equal to IS times e to the power of EV by KT minus 1. Now this is the diode equation, right? And this diode equation is exactly consistent with what we observe in the experimental observations. I mean, if we go back to the concept of PN junction, where we make use of forward biasing. Say, for example, if we rightly remember, we have a PN junction, and then we have a knee voltage, and then we have the rise in the current. So this is my current and this is my voltage. Now this is my reverse voltage. So in case of reverse voltage, it goes like this. Then this is our saturation current, and then we have a breakdown depending on how we are dealing with the PN junction. But here, this equation, I equal to IS, is completely consistent. This is EV by KT minus 1. So if we use this equation for the forward biasing of this PN junction, we can see that up to a certain level there's no current, but then there is exponential rise in the current, which is consistent with this equation, and we can see our current is dependent on some exponential function. So this function is exponential, and we can neglect this minus 1 in front of this, so we can have a reduced equation, I equal to IS e to the power of EV by KT, and from this equation it's clear that we have the exponential rise in the current in the forward biasing of a PN junction. So the concept here is basically we are making use of classical statistical mechanics. So that's a different field of learning for the students. If you're rightly a student of physics, then certainly we have to go through the course of statistical mechanics in an expanded version, and we have just formulated the equations of Maxwell-Boltzmann distributions, and we have used those equations to obtain the diode equation.